Chapter 5.7 starts to talk about enthalpy of formation. And so enthalpy of formation is related to, it's actually not enthalpy of reaction, it's delta H sub F. It's the amount of enthalpy involved in a reaction where you make a compound from its elements in their elemental forms. So, for example, we actually have one up here. If I was making carbon dioxide is made out of carbon. It's also made out of oxygen. So how does carbon show up in its standard form? It starts out as carbon as a solid, a single atom, and its most stable form is graphite. Oxygen, the atom, shows up in nature as an element, as O2, as a gas. And so this delta H, the second reaction, is actually the enthalpy of formation of carbon dioxide. We can also do the same thing for water. We have in here that water we know is made out of hydrogen and oxygen. So we can say, how does hydrogen show up in nature? Hydrogen shows up as H2 gas. And then oxygen shows up naturally in its elemental form as O2 gas. And then we balance it for every 1 mole of that compound. So basically the enthalpy of formation for 1 mole of carbon dioxide is it releases 393.5 kilojoules. To make 1 mole of water from its elements, it releases 285.8 kilojoules. Key thing here is that standard enthalpies of formation, or delta H sub F, and then we have this knot up here, means that this is measured under standard conditions, which is 25 degrees Celsius and 1 atmosphere. And you can find a table of these values for lots of different compounds in table 5.3. It's also found in the back appendix of your book. So let's look at each of these compounds that get made. We want to find out, does the enthalpy change represent the standard enthalpy of formation for these different compounds? And if it does not, what changes needs to be made to make the delta H correct? So basically it's saying, if I wanted to make sodium oxide solid, right here, how do I make it? So let's just practice doing it from scratch. So I have sodium oxide is made out of sodium and oxygen. So we go and we can look at the periodic table. We know that, so just as a reminder, there are 7 diatomic elements, which means they show up in pairs naturally. So we have hydrogen that does it. We also have nitrogen, oxygen, fluorine, chlorine, bromine, and then iodine. And I did it like this because it's kind of like the periodic table. We have hydrogen, and then we have these other ones, which kind of looks like a 7, and there are 7 of them. So these all show up in nature as diatomics. So notice sodium is not on there. So sodium is not a diatomic. It actually shows up as a single element. And we can look at our periodic table in the class. It has different colors for what state they are in nature. So black is equal to being a solid. Blue is a liquid, and red is a gas. So obviously we don't have that on this recording, and you can look up how it is as well, but sodium shows up as a solid monatomic element, one of them, and then oxygen here shows up as O2, and it's a gas. We can see that it's one of our 7. Then we would balance it, making sure that this always has a 1 in front of it. So we have 2 sodiums, so we're going to have 2 right there. And we have only 1 oxygen, and oxygen here comes as a pair, so we're going to need only a half. So now let's go up and check. Does this work out? And you can say, nope, it's missing that half there. So let's do it for potassium chloride, solid. We know that it's made out of potassium and chlorine. So potassium is not one of our 7 diatomics, so it is just a single one. It's a solid. Most metals are solid except for mercury, which is a liquid. And then chlorine is one of our 7 here, so it shows up as Cl2. So to make this, we have 1 potassium, 1 chlorine, so we need to do a half here. Oh, and this is also a gas. So now let's go here. Oh, look we have potassium liquid. That's not right. It's actually solid, and then we should have a half, and each of these should be 1. So a mistake would be to have the coefficient in front of your product being something other than 1. We can't do that. And then here we see glucose, solid, going to diamond, hydrogen, and oxygen. So hopefully you're noticing that's weird. We want to make a single compound, so this needs to be reversed. So we're going to do C6H12O6 as our compound solid. Let's make it out of carbon, hydrogen, and oxygen. So I'm going to have carbon, hydrogen, and oxygen. So carbon is not one of the diatomic, so it just shows up as C. It is a solid, and the most basic form is actually not diamond, it's graphite. That's not always necessary, but that is the allotrope for carbon. So, and then we have hydrogen. Oops, I'm going to put this over here. Hydrogen, it shows up as H2, and it is a gas. And then oxygen shows up as O2, and it is a gas. So the last thing we need to do is balance it. So we have 6 carbons, 12 hydrogen atoms, so 6 hydrogen molecules, and then 6 oxygen atoms, so 3. So we can see that that was right, this was right, this needs to be graphite, and the whole sign needed to shift. So we're going to use this enthalpy of formation. So again, you would find a delta H value for each of these like that, and it would tell you a value and how much energy is associated with making this. All elements in their elemental form, their enthalpy of formation is 0. So that's just good to know. If something's an element, its formation value is 0. So here on this slide, we can see this chemical reaction, propane getting combusted in oxygen to produce carbon dioxide and water. And then we can find all these enthalpy of formations for each of the compounds. Notice propane's a compound, carbon dioxide is a compound, and water is a compound. Oxygen is an element, so all elements have a delta H formation equals 0, which we'll talk about later too. So that's why we don't have a reaction for that. So here's all the enthalpy of formation values. In the textbook, it doesn't show you how they're made necessarily, it just tells you the compound. But we can see now this is the reaction that we're dealing with. So we could use Hess's law, which is really nice, to determine this reaction. So I'm just going to briefly do that for you. You know that we're going to start, here's our goal. So if I want to find the enthalpy of this reaction, I can take all of the formation values and try to manipulate it. So what we're going to do is we're going to say, okay, let's start with red. I need propane. So here propane is a product. I want it to be a reactant. So I'm going to flip this guy. So I'm going to have C3H8 gas going to 3 carbons plus 4 hydrogens, and my delta H for that is positive 103.85 kilojoules per mole. Oxygen's not in here, we're going to skip it. It also shows up multiple times, another good indicator we're skipping it. We're now going to do carbon dioxide. So we want 3 carbon dioxides as a product. Here we have 1 as a product, so we're going to multiply this whole thing by 3. So I'm going to have 3 carbons plus 3 oxygens goes to 3 carbon dioxides, and that delta HF value is going to be equal to 3 times negative 393.5 kilojoules per mole. And then lastly, we're going to do water. Water, we want 4 waters. We want it to be a product. Here it is with 1 water, so we're going to multiply this whole thing by 4. So we have 4 hydrogens plus 2 oxygens going to 4 waters. And so that delta H value will be 4 times negative 285.8 kilojoules. Let's add up our reaction. We have, let's see what cancels out. We have 3 carbons and 3 carbons, 4 hydrogens and 4 hydrogens. We have 5 oxygens here, that's good. And then we have everybody else. So we have C3H8 plus 5 oxygens going to 3 carbon dioxides plus 4 waters. So now we know we added the reactions. We're going to add all of these delta H values. And when we do that, we get our value equal to negative 2200 for the delta H of this reaction. But that was a lot of work. Hess's law can be great, but there's actually another way. The way to do it, if you have formation values, enthalpy of formation values, you can just use the coefficients and do the reaction value equals the coefficient of each of the products multiplied by their enthalpy values minus the enthalpy of the reactants multiplied by their coefficients. So basically it's products minus reactants for delta HF. So let's just pull this over to the side and see if we get the same thing. So I have these values. I'm actually going to pull it up. And we're going to do delta H is equal to products minus reactants. So we'll take our products here. I'm going to say 3 times the enthalpy value of carbon dioxide plus 4 times the enthalpy value of water minus the reactants, which are 1 of the propane and 5 of the oxygens. One thing you're going to notice right away is that you're going to cancel out oxygen because it's an element and so it doesn't have an enthalpy of formation value. So we're going to plug it in. We're going to have 3 times carbon dioxide. It is negative 393.5 kilojoules plus 4 times water, which was negative 285.8 kilojoules, minus, our propane value, which was negative 103.85 kilojoules. So we plug in this calculation and we get the same value, which is actually a misread. It's negative 2220, not 2200 kilojoules. So this, in my opinion, is a lot easier, a lot less work than Hess's law if you have the enthalpy of formation values. So products minus reactants, that's what we're going to be doing for that.